video is an introduction to analytics and machine learning. The whole idea behind the field of data analytics is to make decisions that are informed by your data. So how do you extract value from big data? So what machine learning is automatically detecting the patterns in your data. So what might be some of the driving forces behind the increased use of this? It's cheaper storage and higher capacity, faster communication. It's easier to manage our databases now. We have increased computing power. Today's supercomputer is 40 times faster than the one we had in 2010. But before we dive in, let me give you a little bit of machine learning background. Machine learning is going to convert trends in your data into some sort of logic to automate the data processing. And it's going to be based on pattern recognition with the goal of generalization. Generalization is going to be defined as the ability of the machine learning algorithm to tag labels correctly to data input beyond the examples in the training set. So what this means is use a set of data to make an algorithm. Then you're going to take a new set of data and use that algorithm to figure out what the predicted value would be or whatnot, okay? To be able to generalize into new data that you've not used. But it's based on two key techniques. We have supervised learning and we have unsupervised learning. So big data, that sounds scary, but the hardest part about it is using it. So what is big data? So big data are large and complex data sets. And so there's 3 V's of big data. Volume, meaning we have a whole lot of data. Velocity, the speed at which your data is collected and processed. And variety, meaning that we can have all kinds of different types of data. So data warehousing is going to be that capturing, storing, and maintaining that data. So one thing that's very interesting is we go to the grocery store and they're collecting all kinds of data from us, from our credit cards, from our barcode scanners, all kinds of things. So all of this data is collected. The way we go through it is called data mining. And so that's going to be methods for detection of patterns so that we can make decisions based off the information from large data sets. And so we call this mining the data because you're going through it to get some nuggets of useful information. Effective data mining systems are able to be automated to discover our relationships in our data and predict future outcomes prompted by general and even maybe vague queries by the user. So we have some kind of examples of machine learning would be web searches, spam filters, recommender systems, ad placement, credit scoring, fraud detection, stock trading, or reading handwritten zip codes, and the list goes on. Okay, so how does the machine learning process work? We're going to collect our data and we're going to prepare the input data, train the algorithm if it's a supervised model, then test the algorithm with fresh data, operate whatever machine learning algorithm we're going to use, and then detect maybe subtle changes in our data, such as cycles or seasons, and then measure the performance, and then repeat it every time we need to. And so another process that you'll hear related to this is called CRISP-DM. And so there'll be a separate lecture specifically for the cross-industry statistical process for data mining. And so keep your eye out and we'll watch that later on. And that's kind of the mindset that we want to generate throughout the course. So what's supervised learning? Okay. With supervised learning, the model is going to be used to assess whether an input is going to be a predefined class. So the key thing to supervised learning remains our feature set extraction. So if we have supervised learning, what's your target value classification going to be if your target value is a discrete value? So this is going to be true, false, yes, no, 1, 2, 3, A, B, C, red, blue, green. You would use a regression if your target value can take on a number of range values. So 0.00 to 100.00 or negative 999, so forth. And so here's a little bit of here's a graphic of kind of what supervised learning looks like. We have our training set where our observations are already labeled as dogs or cats. And then we put the data, we run it through the algorithm, and we have a new data set, and that new data set is scored based on the algorithm that was made on our training data set and classifies those observations. And so here, with an unsupervised learning technique, we don't have a model that's generated. Rather, we're really looking at similarities. And so if you're not trying to predict that target value, is it a dog, is it a cat, you can use unsupervised learning. Some popular examples would be clustering, neural networks, or even density estimation. So clustering you would use if you're trying to fit data into some discrete groups. Density estimation would be if you're trying to have some numerical estimate of how strong that fit is into each group. So clustering, you're trying to discover groups of similar examples within your data. And with density estimation, you're trying to determine the distribution of data within an input space. And we're considering all features at that point. Here's our graphic for unsupervised learning. So the key thing with unsupervised learning is that the data does not contain any output information. So all the data is unlabeled. Viewed as a task of spontaneously finding patterns and structures within our data. And it's also viewed as a way to create higher level representation of your data and dimension reduction. So with unsupervised learning, we have all our predictor values being x values and all of our response values variables being y, and both our x's and y's are observed. So this would be a lot of our regression or classification methods. These are going to be most of the methods that you're accustomed to learning in statistics. Unsupervised learning methods are going to be one where you only have x values, you don't have any y. And so you have to use those x values to kind of guess what the y would have been and then build a model from that. And so some examples of that would be clustering and principal component analysis. So when we're looking at our learning the problem, we have our real problem and you're trying to formulate what's going on with it. And you use your domain knowledge as input there, and you collect your raw data and you evaluate your raw data through some exploration approaches. And you can use your domain knowledge again here to get your feature extraction. And then you can apply that to your training data, which you then import into, use to prepare your learning algorithm. And then you take your new data, run it through your learning algorithm, and collect your, and get your predicted y value. So here we have an example where we have a bunch of data points, plotted x versus y in our data set. It's not a straight line, so we're going to estimate the shape of this data using some sort of function, and we're going to call that function f. And then we can calculate the error of this function as the distance between an individual point and that predicted function line. So how do we estimate this function? So we can do this by learning from the data, and the target function is going to be the unknown part. And so we can estimate that for two key purposes, and we do it for prediction and we can do it for inference. So how do we do this? So the first thing we're going to do is assume that we've observed all of our observations in our training set. And then we're going to use our training set and some machine learning algorithm to estimate that function. And using that estimate, we can either use parametric approaches or non-parametric approaches. So a parametric approach is where we're learning that problem and trying to bring it down to a set of parameters. And so this involves a two-step approach. The first thing that we're going to do is make some sort of assumption about the functional form. So we might assume that it's a linear relationship between our variables. The most common one we use is a linear regression model. And then the second thing we're going to do is we're going to use the training data to fit that model. or estimate that function using or the unknown parameters. And once again, we do this very commonly through multiple linear regression, although there are some superior approaches depending on the scenario. So if we look at this example here, and we have income versus education and seniority. So if we said that the most common function that we use is linear regression, if we look at this graph, we see that this is not a flat line. And if we were to make the assumption that it were a linear relationship and we graph it as a straight line, we would see that even if our standard deviation is low, we could get a bad prediction because the model is just not adequately describing all those nuances that we see in our data and all those curves that we see in this plane. So a solution to that would be using a non-parametric method. So opposed to our parametric approaches, we don't have these assumptions about the function. So this allows for us to have greater accuracy to fit a wider range of possible shapes, but we have to have a large number of observations in order to adequately prepare a non-parametric approach to accurately estimate it. So if we were to look at this thin plate spline estimate, we can see that the nonlinear regression methods would be more flexible and can provide more accurate estimates. But the problem with doing this is we can run the risk of overfitting our data, which means basically we're following those errors and noise really, really closely. And so what happens is that error, those noise gets reproduced and modeled when you get new data. Another problem with it is, if you have too much flexibility, you can get a lot of poor estimates for your function. So when we're thinking about, okay, what kind of model do we need to do? Another thing that we need to keep in mind is predictive accuracy versus the interpretability. So conceptually, why wouldn't we just use the more flexible model if it's more realistic of our data? Okay. One of the reasons is if we use a simpler model, it's easier to understand, especially if we're trying to make inferences about our data. Another reason is even if the primary purpose is prediction, it's possible for us to get more accurate predictions when we have a simpler model. But at the end of the day, the thing you need to keep in mind is the data doesn't make decisions for you. You're going to use the data to inform your decisions. So some key things that we need to keep in mind when we're setting up machine learning is that human guidance is absolutely important. The computers aren't going to make a decision about the different settings that you're going to make. You're not going to decide, it's not going to automatically decide for you that this data would be better with a multiple regression versus a decision tree. The quality of your data is absolutely going to be important. So if you have a bunch of garbage data, then your model's not necessarily going to be as solid as you would like for it to be. So make sure you also spend the time cleaning that data, getting to know your data, see if feature extraction is important. But you want to make sure that your model isn't so specific to your data that it's not useful for new data when you get new data. Because if you have an overfit model, that can be really costly and is probably one of the largest mistakes that you can make with data and model. So how does statistics play into this, right? How does that make us make better decisions? Unfortunately, for those of you allergic to math, it comes down to statistics and probability. So I'm compelled to spend some time discussing how statistics coupled with data enables insights and better decisions. So a couple things we need to keep in mind is this idea of statistical inference. Two vocabulary terms. We have a population, which is a set of everything that we could possibly be applicable to the problem that you're looking at. And then the sample is that portion of the population that you're able to get data from. And so what we can do is we can take the data from the sample and calculate the statistics to make inferences about the properties for the population. And so sometimes when you're able to get data from that entire population, you're no longer looking at statistical inference, but you're taking a census. And then a sample survey would be collecting data from a particular sample. So let's think about the process of statistical inference. So we have our population consisting of everyone that's getting a tune-up on their car. Don't know what the average price is, but anyone that could possibly pay for a tune-up on their car. We take step 2 would be, okay, let's take a sample of 50 engine tune-ups and see what's going on. Then, based on that set of sample, we get a sample statistic of the average of being $79 per tune-up. And then we can make the inference that based on our sample data for the population mean would be $79 per tune-up. So before I let you loose on some fundamental statistical approaches, I do need to also make sure we talk about some statistical guidelines, right? So remember, when you're conducting a study, if you have unethical behavior, it can be not taking appropriate samples, or maybe not doing the right analysis because it might take more time, or maybe using inappropriate summary statistics, or maybe even a biased interpretation of your results. You want to make sure that you're reporting facts and being fair, thorough, objective, being as neutral as you can as you analyze and present your data. As a consumer of statistics, you should also be aware of the possibility of unethical behavior by others. There actually is a set of ethical guidelines for statistical practice. It's put out by the American Statistical Association. There are 67 guidelines, and we have 8 topics that they're broken into, and those topics are given to you there. So next lectures that you look at are going to be more into how to actually do the analysis, but I do think it is valuable to spend some time of talking about some fundamental ideas as to where we're going and what we're doing.